out I found out I don't have a microphone or a camera on my computer, and so I'm kind of doing this in a Rube Goldberg sort of way. I'm coming at you through my iPhone, but you're seeing the screen on my computer. So, Doc or Emily, do we need any announcements before we start, or?
I started recording, so
okay.
Ready when you are.
All right, then we'll go ahead and start, and I'll talk about the long range and short range forecasting that we're doing in our EPSCoR research. I'm doing this in collaboration with the climate science team, with most of you in one form or another. Dr. Market in particular, Tim Eichler and Chastity Henson. And why is this? Okay, there we go. All right, so if you want to talk about weather forecasting, we're all familiar with short range forecasting, the kind of forecasting that gets done day to day by your favorite weathercasters. And of course, this forecasting is done in a very physical way. All right, it's done based on dynamic principles, on a closed system of equations that are very highly nonlinear, but we have figured out ways to solve these and ways to model these things or create models and actually get forecasts out to about 7 days. And of course, if we look at short range forecasting, something like 1 to 3 days, a few of us are old enough in this room to remember when a 3 to 5 day forecast of today is probably as accurate as a 1 day forecast back in the day. So numerical modeling and techniques and forecasting techniques have evolved to the point where we've improved quite a bit. So your 1 to 3 day forecasts are quite accurate. And in that vernacular, a long range forecast would be something like 7 to 10 days, the 7 to 10 day outlook. All right, and of course, most of us who are meteorologists know that you don't go too far out beyond 7 days. All right. There are some entities out there which will give you forecasts for 20 days or even 45 or 90 days, the AccuWeathers of the world. And if these forecasts weren't useful, people wouldn't buy them. So somebody must be buying them. But there is a limit to predictability, all right? Thing we call the forecast wall in meteorology. And the forecast wall is about 10 to 14 days, 8 to 14 days, 8 to 12 days, whoever's research you're reading. But the absolute limit is out there at about 14 days. And the reason that it is because of the gases we have in our atmosphere, the size of the very planet we live on, and the fact that it rotates on its axis once every day. And these things present a limit to the equations of motion and how much we can predict, all right? And so a lot of people joke about, well, you know, weather forecasts can't, the weather forecasts are sometimes not very accurate at 5 days. How do we use these in weather models? How do climate modelers use weather models to say what's going to happen in 100 years? Well, climate modeling has a slightly different strategy, and if used correctly, you can make some educated guesses about how the system might look in 2050 or how it might look in 2100. Again, with the proper caveats, but there is some truth to that. You cannot use a weather model to forecast what's going to happen in October or November, December, or something like that. Okay. Now the kind of forecasting we're doing in EPSCoR has been long-range forecasting primarily up till now. We've been doing forecasts 1 and 2 seasons ahead. And for the EPSCoR work, we're primarily doing summertime forecasting, predicting the aggregate temperature and precipitation characteristics of that season ahead. And of course, we focus on the solstice seasons because those seasons should present a more stable climate regime. All right, in the summer, we know it's warm, in the winter, we know it's cold. And of course, the transition seasons being that time when the system is evolving from one solstice season to another. It's too hard to predict what things will do during those seasons. So we don't do a lot of forecasting for those. All right, and our long-range forecasting has been pretty good. We're routinely outperforming the Sept forecasts, and even this summer I thought was going to be a complete bust based on the hot summer that we've had, as well as the amount of the lack of precipitation. But if we look across the state, all right, there's not been a huge lack of precipitation in places like northwest Missouri or southwest Missouri. The biggest lacks of precipitation have been more in central Missouri. But we do these forecasts a couple seasons ahead, and all of this is based on statistics. We look at what's happened in the past. All right. And we use the past to guide the future. All right. And of course, you don't just look at the past as it is. All right. You can take the past and we can look at certain phenomenon that dominate the seasonal weather around here. And one of those things would be the El Nino. The El Nino phenomenon, which involves a change in sea surface temperatures in the tropical eastern Pacific. And one thing that we don't often think about is that sounds like a small part of the globe, but if you look at the area that it encompasses, you're talking about changing the sea surface temperatures in an area the size of the United States or bigger. And that's going to have a big impact on the jet stream. Okay? So we can use the phase of El Nino to kind of guide our thought processes on long-range forecasting, and we'll talk more about that. Now, some of the short-range forecasting issues that we've been getting into, I'll talk a little bit about here. And of course, the idea that the atmosphere has what we call preferred states or teleconnections. These ideas have been around since we've been launching weather balloons and even before. All right, people noticed that when the pressure patterns were doing something out west and in Alaska, when the pressure patterns are relatively high there, that the pressure was relatively low in the east and vice versa. And that this pattern would switch every 1 to 2 weeks. All right, and again, this 1 to 2 week time frame is magic. It goes back again to that predictability wall. And then it was a fellow by the name of Ed Lorenz. And Ed Lorenz used a very simplified model, a very simplified representation of the atmosphere in a hydrodynamic model And he was able to show that within any fluid, not just Earth's atmosphere, there's a limit to how far out you can go and predict with the basic equation. And so that puts a limit on forecasting in any fluid system, whether it's the atmosphere, ocean, or whatever. All right. And I apologize. I'm coughing a lot. I'm just getting over a very nasty cold, and it's been killing me. What Lorenz did in his experiments was use an idealized fluid and looked at a classical problem in physics called Rayleigh-Bernard convection. All right, so his experiments were actually done in a fluid that's even more dense than water. But what he found is that the atmosphere has peculiar characteristics. In other words, you can find in the mathematical space what we call two attracting sets as represented in a entity that looks like a butterfly, all right, the Lorenz attractor that's called. And the Lorenz attractor, of course, is the solution to that equation set that I'm showing on the board, which is just a condensed version of the 7 basic equations. And if you set these equations with certain parameters, you get this kind of what we call chaotic behavior. And the idea is that the weather can be fairly stable, right, in a regime which might be represented by, all right, a trajectory on one of the wings of the butterfly. And as long as you're in that regime, weather forecasting is quite simple. But when you transition from one to the other, all right, that's when life gets a little more difficult because we don't know when that transition is going to occur. Lorenz called it chaos, order without periodicity. In other words, you will have these switches from one phase to another, you just don't know when. And because of the behavior of chaotic systems like the atmosphere, you get this kind of behavior on many different scales of motion. And again, the El Nino is another manifestation of this kind of behavior. Our long-range forecasting is actually very good as long as El Nino and La Nina are persistent. But when the El Nino transitions, or when the La Nina transitions, that's when the forecasts become a little more difficult. And of course, the summer season is traditionally the season when El Nino transitions. And so the fact that we're doing well with summer forecasts during this period of transition is actually pretty impressive. We've gotten some decent results during the difficult periods when the system is transitioning from one to the other. Now, the reason that our forecasts may not have done as well this year is that El Nino was supposed to set in, and it has been. It's just been taking its sweet time this year. All right, other researchers followed along these ideas and said, well, maybe the atmosphere doesn't have two preferred states. Maybe it has a number of preferred states, but the idea of teleconnections was born. And for the meteorologists in the room, that's things like the Pacific North American pattern, again, which describes predictability of the patterns from about Hawaii to the southeast United States. There's the North Atlantic Oscillation, which some of you may have heard of. The Arctic Oscillation, which is one that's been in vogue since about 2010, which describes the vacillation of a jet stream from a more flatter or zonal pattern to a more wavy pattern. And others have taken this idea down to regional scales, looking at the teleconnection patterns that are typical in the Atlantic versus the Pacific. And of course, our European friends are more interested in what's going on in the Atlantic. That's upstream from them. All right, and they characterize the various behaviors and transition paths that these things will take. On the left-hand side is a diagram showing, or a cartoon showing, the various patterns that exist in the Atlantic and the transition paths that they'll take. The diagram on the right shows 9 persistent patterns that are identified in Southeast Asia. And so these ideas have taken on more regional character. And we play off these ideas using the Pacific North American pattern ourselves. Okay, so some of this stuff looks pretty complicated. It is, but the bottom line is it's based on the idea that the atmosphere has 2 or more preferred states, and the transition between one and the other, all right, is the trick in trying to forecast, or is the wrench in the forecast, actually, when we talk about long-range forecasting. Folks have tried to create indices that represent this kind of behavior. In 1986, Hansen created the wave amplitude index, as it shows there. Right, and again, they showed statistically that you get this regime behavior in the northern hemisphere jet stream. Right, it's characterized by a bimodal distribution in the height anomaly field. Again, it's just a statistical representation of what Lorenz did dynamically with the butterfly. Right. And again, as I said before, this kind of behavior has been observed for a long time. All right. Long-range forecasters have been using it forever. All right. And again, to show you that 8 to 10 days is typical, but some of these regimes can slip in as few as 3 days, and sometimes these regimes can persist for more than 35 days. All right, I think it was a couple of years ago, we had a regime persist for about 45 days in the Atlantic, and that led to a long-lived blocking event, which is something that I've been studying. And you can use this index to identify when the flow pattern will switch from what we call a spring jet stream to a summer. The spring flow will have more energy associated with it, just like the winter. You've got those strong temperature differences between the equator and the pole. And again, these transitions that I'm talking about, this tendency for the atmosphere to go from more zonal to more meridional, is just a way that the atmosphere releases built up energy. And of course, in the wintertime, you've got a lot of energy that needs to be dispersed, and in the summertime, not so much. Well, at some point in June, the flow expends its energy and then stays in a lower energy state, representing the summer period. And we've used this index to identify that transition period. And of course, that transition period, whether it happens early or later, can be associated with the ENSO. All right, some of the things that we're doing here with Dr. Market is we're going to talk about a quantity called integrated regional entropy. And integrated regional entropy is just a measure of how stable the flow is. All right. Entropy is a quantity that will derive from the flow. But first we'll talk, because we can relate that to a quantity called the Lyapunov exponent. And a Lyapunov exponent is just a exponent that measures the rate of separation between two systems that are initially close together in character. Right? If I have two systems that begin very close together, they may stay close together in time. They may evolve close together in time. Or they may separate slowly with time. And one state goes to a vastly different outcome than the other. You can measure this with a Lyapunov exponent. And a Lyapunov exponent is just an exponential that comes from the solution to a simple ordinary differential equation, which I put up on the board there, the change in x of time equaling some quantity times x, all right? You solve that equation, all right? The solution is going to be C naught e to the negative lambda t, and negative lambda represents your Lyapunov exponent. Now that last relationship that I put up on the board, where I solve for lambda, all right, gives you an idea of the size of the separation between your initial state, all right, and the state as it evolves at some time t later. All right, so that can measure how much separation there is. And again, this tells us something about the stability of the flow. If these exponents are positive, it means that two flows that are initially similar evolve very differently in time. All right, and this again is the characteristics of a chaotic system like the atmosphere. It's a quantity called sensitive dependence on initial conditions. And the larger, the more positive that Lyapunov exponent is, the more separation you'll get from an initial system in time as you go forward. And it's also a measure of stability in that sense. All right, the bigger that exponent, the less predictable your system is. All right, so a little bit about differential equations, and we're also doing some research on in a different area where we're talking about a quantity called rough dependence on initial conditions. As it sounds like, it basically is talking about those hopeless forecast situations. Well, we can relate this quantity, this Lyapunov exponent, to meteorological variables. And one that we relate it to is the measure of entropy, which is the square of vorticity. Now, for those of you who aren't meteorologists, you know that, or for those of you who are meteorologists, we know that we often talk about vorticity as being spin, all right? It's really a measure of turbulence, but it's atmospheric flows that are doing something like this, circulating. And you square that thing and you get a quantity that's relatable to the positive Lyapunov exponent in the atmosphere. Okay, and we've used this quantity quite nicely. All right, the idea that we initially used this quantity for was to find the onset and decay of a phenomenon called blocking, which I'll talk about later. But in the course of that research, that idea failed. And it failed because this quantity, integrated regional entropy, can really identify any flow transition. All right, when the atmosphere transitions from a more wavy, more meridional flow to a zonal flow, or vice versa. So it works quite nicely to identify those transition periods. When this value gets large, again, large Lyapunov exponent, less predictability, transition, right? That's what we can identify. when this quantity goes down, all right, and is less, all right, that's a period when things are more predictable and more stable. A good example of this was the winter of 2013, 2014. All right, you could measure the integrated regional entropy of the atmosphere as a whole, and it showed a transition toward blocking flow in late January. And then at the end of February, it showed a transition out of that flow. But during that mid-period, there was a transition from very high amplitude flow, which you can see in the diagram on the right, where the average northern hemisphere heights were and pressures were relatively high, to where they got very low by the end of the period. All right. And again, the onset of this blocking event was identified by this IRE, but that was also the transition from a more zonal to a more meridional atmosphere at the time. And then sometime in early February, the flow transitioned back to zonal flow, which we see in the diagram on the right. All right. And in this case, these periods of time correlated with the life cycle of a Pacific blocking event that dominated that year. If you remember, that was a very cold winter. Blocking, when it occurs in the East Pacific, is responsible for cold winters around here. All right. It allows for Arctic air masses to come invade the central U.S. with more regularity. All right, so we can use this to identify flow transition, and then it's quite possible for us to exploit this quantity in the future, maybe to do some forecasting at the subseasonal level. So we're at the beginning of this research now. We're at the point now where we're identifying flow transitions, all right? And our research is identifying them quite well. And again, the utility of this in the future is you might be able to do some subseasonal forecasting, like anticipating the need for periods where you might have to water crops more, or you might be able to anticipate when you can fertilize or things like that. So there would be some agricultural applications for such short subseasonal forecasting. All right, as I said before, Newberry, as I said before, we've used this to identify spring to summer transitions. All right, in some years they show quite well, like in 2008. You see a very strong drop-off in entropy right around the midpoint of this graph. In 1971, you can see a more gradual drop-off that happens in the early part of this year, from around May 1st to the early part of June, and then boom, you drop into a lower energy state sometime in mid-June. So again, it has nice sub-seasonal usage. Right. And if we look at 1971 and look at various flows, all right, from left to the left side is the middle of May from 1971. Then you have late May to mid-June 1971, and then mid-June of 1971. And of course, in each case, the flow over the United States is a bit different, right? And these were associated with changes in the value of IRE. all right, at the cutoff times, at the middle of the cutoff times, some high values around late May and then mid-June. And in summer of 2008, showing a vast difference in the flow over the USA. From early June, when you had a trough ridge pattern over the USA, to a ridge trough pattern by late June. And if you want to see some of the real-time applications of this research that's being done, the website is given there. All right, it was designed, the website was designed by our own Dr. Patrick Market. All right, and we plot daily plots of this value as calculated by a model. So it's each of these plumes represents a 10-day prediction of this quantity. And you can see in the left-hand diagram here for March 2018 that the forecast from one day to the next was very consistent for a long time and projected a switch in the northern hemisphere flow around March 10th, right, which did happen. And then another switch in the flow regime around March 16th to 18th, which also happened, if you remember, late March to, actually from late March to mid to late April, it was fairly cold. And the IRE identified these things quite nicely. All right, we had a huge changeover in flow regime in end of April, early May to a much hotter, much warmer period of time. All right, in early May, things settled down for a while. And then in late May, you had the onset of almost a semi-permanent summer state throughout May, June, and July, all of which have been very warm this year. All right, so that's some of the work we're doing with IRE. To go back to seasonal forecasting a little bit and talk about some of the things we've done, there's 4 ways to do seasonal forecasting. You can forecast that the next season is going to be climatology, which means the average of the last 30 years. That's actually a pretty tough forecast to beat. All right, if you look at the statistics of climatology, all right, it's pretty tough to beat climatology in long-range forecasting. You really have to be able to forecast extremes to beat it. And that's especially true in the summer when the variability in the atmosphere is much lower than it is in the wintertime. Persistence can also work. Persistence is a way of just saying, well, if this month was 5 degrees above average, next month will also be. All right, and that works pretty well if your flow regime is pretty stable. Analogs is a way of just saying, wait a minute, I saw this before. And the last time I saw this, it evolved in a manner that where X happened next. So I'm going to predict that the same thing is going to happen. Actually, with the Hurricane Florence, all right, if you looked at the path of Hurricane Florence, it followed a path very similar to Hugo. All right, and of course, Hugo did what many hurricanes do. It came into the coast, hit the coast, and got picked up by the jet stream and went out to sea. And so the path of Florence started off quite analogous to that. And the only difference is that many of the models were forecasting Florence to do some weird things, like like hang around in the Carolinas for a few days and dither off to the west or to the south and not recurve back to the north. Although the models are finally calling for it to recurve to the north more now. So analogs are based on forecaster experience, but now that we have enough computing resources, you can actually put in a pattern today, search for patterns in the past that were similar, and then look at those. Now that we have computing power and data, this can be an effective tool. And then contingency, which has been the bread and butter of what we've done in our long-range forecasting, saying that, okay, we'll look at the past statistics, but we'll base those statistics on very well-known patterns like ENSO and the Pacific Decadal Oscillation. The El Nino is the 800-pound gorilla of interannual variability. It's why one year can be very different from the next. All right. And also atmospheric blocking. When I teach long-range forecasting, I say if you know El Nino and southern oscillation and blocking, you can be a very good weather for a seasonal forecaster. Blocking is prolonged ridges that are relatively stationary in the jet stream for a period of 8 to 10 days on average. And where have we heard 8 to 10 days before? All right, in the average lifetime of flow regimes. All right, so blocking and flow regimes are closely related. Some papers that we've published on things that we've done are the Henson paper, where we looked at the ENSO and PDO related variability, and we were able to tie that into crop yields, and we got that published in the International Journal of Biometeorology. We followed that up by comparing what we're doing and seeing if it will work in Southwest Russia. And based on their patterns, and guess what? It works. This is a paper we wrote with Doc's help, looking at the idea of Pacific teleconnections and their ability to make, and our ability to make forecasts in the 2 to 3 week range. That's where there's a lot of research being done right now, is making forecasts in that 2 to 3 to 4 week range. Forecasts have been made monthly forever. Seasonally now, they've been made for a while too. And then of course, short range forecasting is that 8 to 10 day period. All right, so to bridge that gap, right, is the 2, 3, and 4 week range. A lot of research is being done on that right now, using a mixture of dynamic approaches and statistical approaches. Blocking, yes. If you look at the impact of, I don't know why I said seasonal range blocking. I guess I had blocking on my mind at that point. The Burkett paper set down a lot of the analysis for what our forecasts are based on. He analyzed monthly temperatures and precipitation, not only for Missouri, but for the Midwest in general, from about Minnesota to Louisiana, and from about the plains to the Appalachians. And we looked at the primary ENSO variability and PDO variability in those regions. And we used techniques like Fourier and wavelet analysis. Our summer forecast for 2018, of course, was based on the idea that La Nina was fading at the end of February and into March, and it lingered a little longer than we thought. It lingered a lot longer than we thought, actually. Most of the forecasts dynamically and intuitively were pointing toward an El Nino onsetting during the summer. And usually when you transition from La Nina to El Nino, our past statistics have shown that those are actually pretty good summers agriculturally, a little milder in temperature and a little more precip. As we know, that did not happen again, and that's because El Nino has taken its sweet time to develop. But at the time, before the season began, again, the model guidance was pushing things toward El Nino. And so that's what we did. We had forecast based on that. All right. And of course, the work we did with Henson et al. Individualized, or not individualized, but made the forecast down to the various climate divisions for Missouri, of which there are about 6. The climatic conditions in Division 1 there in northwest Missouri are pretty similar for these counties. Not only are the climate characteristics similar, but the interannual variations are similar in that region to each other. Right. So we made our forecast based on that, and we looked at climate and yield data within each region and tied that together, and we had come up with a forecast for summer. And it'll be interesting to see if the corn yields are actually above normal as we had forecast. My guess is they're not going to be. I've heard off and on throughout the state that yields aren't quite as good, and that's again because the forecast was a bit off due to El Nino's pokiness. And again, that just shows you some of the limitations of trying to make long-range forecasts. The atmosphere can look like it's going to do one thing, but it may throw you a curveball. All right, atmospheric blocking. All right, we've done a lot of study on that, but again, it's the reason why when we get a cold winter around here, that's due to blocking in the upstream part of the flow in the Eastern Pacific. You look at the winter of 2013, 2014, 2014, 2015, blocking in the Alaska region. So the hot summer of 2010 in Russia, again, prolonged blocking. So it influences a season. All right, let me wrap this up. I might be talking a bit long, I don't know. We're looking at, we've done some work in short and long range forecasting, but either one is based on a dynamic understanding of the atmosphere and its properties and its behaviors. Right? The behaviors of the atmospheric dynamics and how they influence predictability. All right, early work showed that the Northern Hemisphere generally has 2 predominant modes. That idea still exists today, but you can regionalize it. Seasonal range forecasting. Again, El Nino is the 800-pound gorilla of that for our region, especially since we're closest to El Nino in the upstream. If you look at the general circulation on an interannual time scale, the weather in North America is the most variable on the face of the earth. We're getting better at this. Despite the setback this year, we're getting better at this. We predicted the last 6 summers straight pretty well. And of course, we've done some research in linking the weather and crop outputs, and that's also been valuable for producing crop forecasts. This integrated EPSCoR has been a great tool to use for sub-seasonal forecasting, and it's based on the dynamic character of the equations that represent atmospheric flows. And it has utility in identifying these regime transitions, and we've got a nice website to show that. And it's also allowed us to partner with some folks who are interested in this kind of weather forecasting. That's the Weather Prediction Center and NOAA and some others. So again, I apologize for all the coughing, and again, I'm getting over a cold and a fever, and it's been pretty miserable all week. So if anybody's got any questions or comments, and we have time for a few, I think. Otherwise, you can email myself or Dr. Market, and we can answer your questions. And again, I apologize that the camera's doing a lot of this, isn't it? Sitting there holding my iPhone. Well, I either put everybody to sleep or or at some point the sound cut out. No questions? Okay. All right, thanks.
Thanks, Tony. This is Emily.
Hi, Emily.
I'll stop the recording.
Okay.
Okay.